In this part, we're gonna show you three kind of scenarios. Like pass statement. If we create a pass statement, but there are some issue over. There are some typical issues. The first one is the curve. The curve we wanted the tool to manipulate is quite different between the curve on the surface and there's an offset. I mean, there's an offset between the curve and the desired path. So what we can do, we can tell you later. And the second one is interference. It means that there is a curve, but we found that there are some collisions effects during this curve, so we can modify the position, the orientation of the tool. And the final one is the reason why we have to create a user frame. It's because if we found that the product is the position is too far away from the robot, we can relay out the program, the process, so we don't have to adjust the point every time we relay out the product. First, if we want to let the robot to process at the middle of this position, we can directly use the offset to adjust the robot movement, that is, so the robot can be walk on the desired path we want. For example, there's a gap between that, right? The only CAD file, CAD feature we can get is here. Reverse it. But ideally, we want to have a curve. We want to have a path at the middle of the face, so we can use the side offset to directly modify it. Sorry, -2 will be fine. This one, for example, like this, so we can get a path by using side offset. Okay, it is the first scenario. And second one is interference. So during the robot movement, there might be some points may have a collision result. So what we can do is adjust the orientation of the tool and jog the position one by one to confirm that the collision is happening or not. So I can use the collision detection function over here. We can click the collision function over here, and then I want to process this one. This is speaker, and also I want to check with the tool head. So this is the tool head, and I want to have a collision detection result in simulation mode and also the programming mode. So which means that if you if you use the simulator, you can find that there is a collision and stop the simulation during the process. And secondly, if you active in program, it means that if you're using jog, you can directly get the collision result. Speaker. For example, if I want to run from this statement, okay, I can find there's a collision issue over here, but it's not. I think it's not the main one I want to show, but I can increase some. Okay. Of course, I can multi-choose the point and use the object mode to make it go upward. You can just modify the tool path from here, and then, or we can adjust the orientation. I think over here, there are so many collisions right here or here. Okay, from this point, the tool gun already touched the product, right? So we can directly modify the path, check it again, still have some collision, so we can adjust some points to resolve this problem. Yeah. Okay, the third scenario is if we put the product too far away from the robot, we can directly modify the position of the product, and we don't have to reprogram again. The process should be work well after we move the product. For example, if I have a bank case over here, and I want to modify the position and run the bank test. So we don't have to do anything else because the system will detect the user frame on the product to give the right position of the robot. Okay. Okay, let's go into the final part. After we establish a lot of points and a lot of robot movements, we can export this kind of points table and also the UI program to our real robot. First, we can use the delta point table from DIATwin. And there is an export button here, so we can directly output the whole point table from DIATwin. And later on, we can use the DRI Studio, for example, and create a project, And later on, we can use the point. We can enter into the point, and there is an import. There's an import button over here, so we can directly import the CSV file that DIATwin generated. And second, we can also export the Delta language robot language file, the Lua file. So the program will be the same with the Delta robot. We don't have to modify the process again. We only have to make sure that the user frame will be the same with the virtual environment, which means that if we output a project by maybe user frame 1, the only one thing we need to do is to calibrate the user frame on the real robot, so we can directly run the whole simulation without any problem. Okay, let's give it a try. It's pretty simple. You just have to click the export button over here. There's a Delta point table for test 2, this one. And the point will be export in the Delta point table format. And the point will reference on the user frame we just create. So that is the reason why we focus on user frame so much. And finally, we can export the Delta robot language file over here also. So we already set some user frame, set the user frame index, set the tool frame index. So we don't have to. The only one we have to take care about is the user frame on the real machine. Okay, because when we export this kind of frame, this kind of user frame, it's just ideally it's just a golden sample. But for the real robot, we have to take care about how to calibrate the user frame. Okay. Now homework. It's a really simple homework. Don't have to worry about it. Just open another file. It is the past STEM homework. It's really simple, I swear. There's a past STEM homework over here. The only thing you have to do is create a path on each product. That's all. That's all. Whatever you want. You can have a Delta logo here. You can have a curve over here. Whatever you want. Yeah, that's all. And you can the homework you have to upload is just the DTL file. You can directly save the project in DTL file and upload to our OneDrive server. That's all.